Okay, good afternoon and welcome to MAE 106. My name is Richard Kaur, and this is lecture 23, Probability in a Uniform Sample Space. And we'll also cover the axioms of probability theory. So last week we had our test 2, where we had gone through sets and counting, some counting. And we'll have a little bit more on counting in this unit as well. I'd like to say good afternoon to everyone in there in the chat. Thank you for, hopefully you can hear me okay. Grab my ink here. Loud and clear. Good. So let's start off with the title, of course. So this is lecture 23. Probability in its uniform. And don't worry about if we don't know what, that's the whole point of having a title. It's just to kind of identify what we're going to talk about today. Sample space. So we have already seen what a sample space is in the previous we can hear okay. I felt confident about the second test. Excellent. That's good to hear that people, yeah, the whole point of the test should be to show off what you know. All that hard work that you've done by doing the exercises and listening to me during the lectures should all pay off. Uniform sample space, and then it's probability. I still remember there was yeah, that's good to see that people finished the test. Good. Before we start, I remember watching a Netflix special. If you ever get a chance, it's called Vegan on His Way to the Complaint Store. It's with Eugene Merman, and he kind of does a little bit where he says, I filled out a thing online where I became a minister and can marry 40, I can marry people in 40 of the 50 states. He goes, I don't know which 40, but chances are this is one of them because that's how chances work. And, you know, if each state was equally likely that he was going to end up in, yeah, he would have a 4 in 5 chance or 80% chance that he probably was in a state in which he could administer a marriage license. So let's start off with what a sample space is. We knew that from our last lecture. Sample space. So it's not like the things that you get at the store where you go up to and you grab all the samples. That's not what we're talking about there. We're talking about, in particular, it's the kind of universal set. It's kind of like the universal set. It's all the possible outcomes blah 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 of interest in an experiment. Somebody is writing, those are good odds. Never tell me the odds. A man of culture. So we have sample space. So then if you add in this word uniform, I don't mean, you know, like the uniform that you're probably wearing. Yeah. That's not what I'm talking about. What this means is kind of like uniform inconsistency, uniform in that it's the same. I guess it could be in relation to clothes, but not the actual physical clothing itself. It's actually to meaning that the same or we can say is equally likely. So when we put that together, uniform and a sample space, basically it's a sample space where the outcomes are equally likely. So, for example, we could have we could say a fair die. And this means like a die is a dice, or one of dice, right? So it's like it's a cube, and it has those little pips on the side of it, and that each side is equally likely to show up. You could flip a two-sided coin. So again, here's like a coin. You know, there's heads, there's tails, and we're going to assume that, you know, each side is equally likely. So again, there's kind of the assumption that, like, okay, if I flip it, oops, and of course I flipped it too far outside of the camera. Oh well. So I kind of flip it, and it lands here. Okay, that's good. But it didn't, like, land on its edge. It didn't land on the edge and, you know, roll away or do something silly. So that's kind of flipping a coin. Okay. What else? Selecting a card from a deck of cards. You know, here we go. Here's a deck of cards. Ooh, Bicycle. Good brand. They're not sponsoring this video. Get rid of the two jokers. And so each of them are equally likely for me to pick a card. So you can pick one, and I won't get to show it to you. Okay, so those are like three common examples that we know of for a uniform sample space. So if we have a definition, here's the probability of a sample space, a uniform sample space. Okay, so we have an event E. And the probability that's associated with that so P of E, so the probability of E in a uniform sample space is, so we have the probability of E. Now I want to know what that card was. It could be any of the 52 cards. So the probability of E is the number of elements that are in E over the number of elements in S. So just in words, it's the number of sample points in E. Oh, did I? Over the number of sample points in the sample space S. Okay. So kind of here's the Venn diagram for this. Here's your uniform sample space S. And so you will have a whole bunch of elements. You'll have some sort of set. So let's draw a set. Let's say here. There's E. So again, in this assuming that this is S is a uniform sample space, the probability would be the number of elements in E, so this is 1, 2, 3, out of, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Hopefully I counted that right. Good. So the probability of me selecting one of those points inside of that sample space, assuming that they're equally likely to occur, that it would be 3 out of 11. So here's the example. So the experiment is flipping a fair coin. So then our sample space would be, we can either have heads or we can have tails. And there's that assumption that it's fair. So from that, the outcome is equally likely. As it is tails. So again, if H means heads and T means tails, the probability of flipping heads would be the number of times in the sample space. So number of times it would be in H over the number of times it's in T. Sorry, it should be S. So here is head, there is tail. And those are the two elements in there, and this is the set. So you would have, here's your event, there's the other event set. So again, there's only one element in H that we want, and there's two, so it's just 1/2. I know that this might seem a little obvious since this is probably something that we would have seen in elementary. But let's start off with the example that we do know, and then we can try to extrapolate this. So in this case, we would have tails for the probability of tails here. Okay, so again, this is very easy when the sample points are all equally likely. And to be more explicit, this means that no outcomes in the sample space are more likely to occur than another. This would exclude experiments with a non-uniformly weighted coin. So like if this was a trick coin or something in which the distribution of the weight is not evenly distributed, then it won't land on heads or tails equally. So we want to avoid something like that if we're working with a uniform sample space. Okay, so let's do an experiment where I'm going to pick a card. So in that case, my sample space would be kind of that. I can have an ace of diamonds, I have a 2 of diamonds, dot, 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 so on and so forth. There's 52. All right, because there's a lot there. Got all those different cards. So these are all kind of well shuffled. Okay. And what does this mean? That the number in the sample space is 52. And we're going to say, what is the probability that I picked an ace? Okay, so it doesn't say that I picked a specific ace, like an ace of hearts, an ace of diamonds. It says any ace. So what does that mean? Well, okay. It means here is my sample space. Here is the 52 cards. And it means that, so I have 52 in total. So what we should do then is I'm going to say that let E denote picking an ace. So then the probability of this event, E, is the number of outcomes in E over the number of that are in the sample space. So I already know that this is 52. There's 52 cards in this deck. And then I need to find, since each of these cards are equally likely, I could pick this card. Here's one. I could pick another card down here. These are all equally likely for me to be chosen from. So what I do then is I go through the sample space looking for the things I want. So I'm going through the sample space. There's one. So I have 2 so far, right? And you're scanning through the entire sample space. Another one. Okay, so we've gone through the entire, all these points, sample points, and we come up with 4. So you can then write down that the number in E is 4. I can explicitly write them down because it's quite easy for me. In this case, I have ace of hearts, I have spades, diamonds, and clubs. So again, so the ace of spades, the ace of hearts, ace of club, and ace of diamond. So I have 4 out of 52, or we can reduce this, we can reduce our fraction so that it's 1 in 13. So again, the chance of me picking an ace out of this deck of cards, if I had these shuffled and that each outcome was equally likely, is 1 in 13. Okay, seems straightforward. So this is the end of that exercise. Here's the end of this example. Switching to a new piece of paper. Okay. Sir, when can we expect our test 2 grades back? I expect to have them back within the week. Okay. Yes. Yep, I'm just working my way through them. Okay, so let's do a little bit of let's do a simplified code check problem. Okay, so there's a fancy restaurant and there's a famous mathematician by the name of Montmort, and he goes with 2 of his friends and he checks in their coats. But there's an incompetent attendant and he didn't affix a ticket number to each of the coats. So when Montmort goes back with his friends and goes to collect their coats, the coat check stubs are useless. So what ends up happening is that the attendant hands back the 4 coat. Oh, so we're going to go with 3. So let's do. So we have Montmort. He's a mathematician. And he has 2 friends. Okay, and they have, so there's Montmort and then 2 of his friends. And they have they have their little coats, but the tickets that they were given, the little stubs, don't match what the coat was. He didn't fix it. So they're kind of useless. So are useless. So the attendant hands the coats back to each person randomly. Okay. So then the question becomes, what is the probability that they are handed back the correct coat? So the first thing that we should be thinking is that, okay, well, first of all, we'll assume, again, here's our assumption, assume that all outcomes are likely. So Puffin is saying 1/3, 1/3, 1/3. Is this assuming that they're not other coats from outside the group of 3? Yes, that's a good one too. The 3 coats belong to the 3 friends. So we could do the same thing again. You have 3 people. How many ways can you assign then the first coat? Well, there's 3 choices for that first person. And then you're left with 2 for the second person. And then finally, you're left with 1 on the last person. So 3 times 2 gives you 6. And assuming that you have them all in the correct order, there is only one correct order. Therefore, the probability is 1 in 6. Does that make sense so far, what I've done? So, I mean, we could write out all the possible ways. So assuming that 6 ways of distribution S, but the E, there's only one of those 6 exactly. So for instance, let's say that this person up here, let's say that the correct order should be, for this person should be A, then we'll have B, and then over here we'll have C. So that should be the correct order. So there is only one way to hand out those coats, A, B, C. That's the correct order that we want. But there's so many different ways, there's 6 in total, that we could have. You could have A. So again, what is the probability that they are handed the correct coat? So what I should add on this is that they are all handed the correct coat. Okay, so we can do A, C, B, A, need to go with B, A, C, B, oops, C, A, oops, there we go. So hopefully Mr. Puffin has the right, that I said yes to the answer. So I have BAC, BCA, 4, CAB, CBA, 4, 5, 6. So hopefully I have all of those. So again, there's for them the probability for them all to be handed the correct coat. There's only one there. So again, E is the event that they are all handed the correct coat. Okay, perfect. So then the probability of that is the number that's in E over the number that's in S. There's only one correct way to do that. So that's the ABC. So there's only 1 out of 6 to do that. Now we can change this and we can modify this a little bit by saying, what is the probability that only one person gets the correct coat? Okay, so what is the probability that it gets one gets? So let's say that F is the event that one person gets the correct coat. So now what we can do is we go through what we had in our sample space. So ABC, that would, we should read this very carefully. If we say that only one person gets the coat, ABC doesn't count because all 3 are them. We just want to get where just one person is getting it correct. So ACB is okay. So because A got the coat, but not C or B. We have BAC, so the C person got the coat, so that's okay. BAC. We have BCA, so none of them got it. CAB, none of them got it. And CBA, none of them got it. So this is the case where A got it, C got it. I feel like B should get it. So there's CBA. There we go. Yes, thank you. Right, and that should, this is the case where A gets it. This is the case where C gets it. And there's the case where B gets it. You got it, yep. So then the probability would be, probability of F is the number of, in that event F, out of the sample space. So this would be 3 out of 6. So the probability is 1/2. And this can also change again. We can also push this question a little further again. We could say, what is the probability that at least one person gets the correct code? So again, be very careful about reading this. This says at least one. So that means from that, you know that you could have cases. You could have one person, you could have two, or you could have or all three. Get it? I'm not sure yet if it's 2/3. Let's work it out. So if I let this be G, is the event that at least one person gets one coat. So I'll kind of write out. So now we go back to the sample space, we look at it. I have ABC, so again, that one has at least all of them get it, so that's okay. I have A is getting in their code there, so that's good. This one, C is getting their code, so that's okay. B, C, A, none of them get it, so not that one. C, A, B, none of them are getting that one. Oh, sorry. And the last one, CBA. So just to check with the class, are these all the possibilities where at least one person gets the correct code? Perfect. Okay, so then we can do our probability. Yes, okay. I think, Puffin, you're right. So again, if I go to the number of sample points that are in G, so there's 1, 2, 3, 4, over the number in S, so 6. So I get 4 over 6. And reducing that down to a lower fraction, I can divide by 2 on both the numerator and the denominator, so I get 2/3. So therefore, the probability that at least one person gets the correct coat is 2/3. Or you can think of that as 67%. 2 out of 3 ain't bad. Yep. Okay. Not bad. So you can already see where we'll start to head into using what we had learned in our previous units with sets and counting, because we have a whole bunch of ABC, ACB, BAC. These are all different orderings, right? Or we can think of these as permutations. So instead of us having to write out what I call the brute force method of enumerating or listing out all the possibilities, wouldn't it have been better if we had been able to use our multiplication principle? We had 3 times 2 times 1, which gave us 6. We knew that we only wanted one correct order, and that gave us the 1 out of 6. That's where we'll eventually head to. But first, we need to define probability a little better. There's 3 axioms of probability that we need to discuss. Okay. So the word axiom, it's kind of, we usually mean this in math to mean a statement that's regarded as an irreducible fact that is self-evidently true. We use axioms like atoms when we thought that atoms were the smallest building blocks. So that's what we mean by axioms. These are kind of the fundamental, self-evident truths. Okay. So what I'm going to use is kind of Venn diagrams / I'm going to make it, instead of using like rectangles or something like that, I'm going to use a square. So here's a square. You can think of it as a probability square, what have you. There we go. So some people have called this like a probability picture, or in the textbook, I've called it an ichthyogram. And ichthyo meaning probability, and gram meaning a picture. But all it is that I want to say that this is a 1-by-1 area. Okay? But it's a square. So axiom 1 says that the probability of the entire sample space is 1. Okay, so if I look at the ichthyogram, I've made a square, it's 1-by-1, so I know that this entire area is equal to 1. I'll write down 1 by 1 is equal to 1. Okay, so if you think of the sample space as a square, the entire area of it should be 1. Okay, simple enough. Here's axiom 2. So I still have, let's say I draw my square again. So there's my sample. Here's 1 by 1. Okay, so if you're thinking of it in terms of area, it means that if I had some event inside of here, let's say if I draw some event here, this would be like, we could say that this is like E okay, so that would be like how much E is, and that area inside here would be the probability of E. So in this case, it'd be, you know, whatever it is times 1, which gives you probably 1. But because we have area, the smallest amount of area that you can have for an event is 0. And it's always going to be positive. It can be 0 or it can be positive. So this leads us to our axiom, which is the probability of an event has to be greater than or equal to 0. And that's it. We can make it a positive number. We can draw this so that it's just a line, and so that's 0. The area is 0. So that's fine, but we can't have negative probability. Okay. And the other thing too is that I can't have an event that is bigger than this ichizogram. I can't have it bigger than the sample space. So because I'm limited by the sample space size, which is 1, so from axiom 1 and axiom 2, which says that the event has to be greater than or equal to 0, then it follows that the probability of the event E must be greater than or equal to 0 and must be less than or equal to 1. So it's bounded between 0 and 1. So let me just kind of box these as we go along. It's funny because we're talking about a box itself. So again, from 1 and 2, this leads us to that an event, the probability of an event must be between 0 and 1. Okay, which means then that we kind of have a way of describing events. Between 0 and 1 is kind of the probability of the event. And from 0, we say that this is impossible. And at 1, we say that this is certain. And in between is probability. So you can think of it as like a numerical scale. Okay. And the last one. So we've done page 4. Here's axiom 3. Okay, so again, I'll draw the square that has length 1 and 1. Okay. So axiom 3 says that if I take these let's split up the whole sample space. Let's say that this is E1 and this is event 2 and up here is En. I don't know, there's n many. So like here, that's the probability of E1 because that's the area. Let's say over here, this is the probability of E2. Here's the probability of En. So what we're going to say for this axiom is that E1, E2, En are what kind of sets or what kind of events have I drawn here? They're not overlapping, so therefore they're called what? Discrete. Yes, yes, there's countably many. Mutually exclusive is the term I was looking for, yes. Mutually exclusive. Okay, so if they're mutually exclusive, then the probability of the union of the events is equal to the probability of each individual event occurring. So what I mean is that if I took the union of these, E1, E2, the union all the way up to En, and these are mutually exclusive, then that is equal to me just adding up the individual probabilities of each event. So again, if the areas of every event do not overlap, then the union of the events is found by adding them all together. Okay. So those are the three axioms of probability, which is the probability of the entire sample space is 1, that an event has a probability that is non-negative, so that the probability of an event is greater than or equal to 0, such as this. I can't draw anything less than 0. From 1 and 2, I get that an event must be between 0 and 1 for probability. And that if the events are mutually exclusive, meaning that there's no overlap of the areas, then if I want the union of it, I just have to add up the individual probabilities. So that would probably be a good test question or an exam question, which are, what are the three axioms of probability? Okay, so are there any questions about the axiom rules before we move on, or the axioms? Maybe it's something I've forgotten, or you need some clarification. Okay. So, here we go. Let's start off with a simple rule. Under axiom where you wrote fundamental, you forgot to write AM. Okay. Okay, thank you. It's great. I don't have to have a spell checker. People keep worrying about paper not having spell checker. No, it's if you have other people watching, then you don't have to worry. It's great. We should keep using paper. Now, I've drawn a keys-o-gram. Here is a sample space, and I'm going to draw, let's say here's an event E. And so this area in here is the probability of E So here's the complement rule. So what's the probability of E complement? Well, the nice thing is over here, I have, here's my set E. We see that the area is the probability of E. So then the complement should be this white space up here. Here's E complement. Which means that this area over here, exactly, this is the area or the probability of E complement. So yes, so how can we figure that out given that we know what the probability of E is? Well, we know that the entire space has to be 1 minus, so we're doing basically, we're thinking indirectly, right? We're starting out with all the things that we know, and then we're going to take away what we don't want. And in this case, we don't want the probability of E. And that's it. Okay. We can do a little proof for this. So this is kind of the picture for it. But we can also do kind of a proof. Here we go. So we have two events. We have E union E complement, and that is the entire sample space. And you can think of that as part of the set rules that we had, or set operations / rules. Remember when we said that we had A union A prime, or A complement, is equal to the entire universe. So we have those two events. So starting out with that, we can have the probability is equal to 1. That's axiom 1. We know that S then is equal to E union E complement. There we go. So we've done this by 1. This is just by using what we had up here. We know that these are mutually exclusive events, so that by axiom 3, I can just sum the union of them is just the sum of the individual probabilities. algebraic manipulation, bringing this to the right-hand side, I get 1 minus the probability of E. And we're done. So what we had previously, we can go back to using our card experiment where we said what was the probability that I picked an ace. It was 1 in 13. So not selecting an ace from a deck of cards. We had that the probability of E, which was selecting an ace, was 1 in 13. So then the probability of not selecting an ace is 1 minus 113, which means that there's a 12 in 13. 12 over 13. So therefore the probability of not selecting an ace is 12 over 13. Okay. And this one is called the addition rule. Okay. So what ends up happening is that we could have the probability of E union F so if we think back to a Venn diagram, here's E, here's F, and here is the sample space. So we can add up all the probability that's in E. So there's the probability in E. So there it is. Then we can add all the probability in F, so all the area. So but what we end up having done is we've overcounted in this intersection here. So we need to then remove that area or that probability where it intersects. So the probability of E intersect F. Okay, so what we can do is, let's do an example. So again, this should look fairly familiar because we had done the principle of inclusion and exclusion, where we said that, instead of me using A and B, I'll use E and F, that the number of in E union F is equal to the number that's in E plus the number in F minus the number of elements that are in E and F. So what we can do is, let's say that what is the probability of an odd number or a number greater than 2 when rolling a fair die? So we should work out what our sample space is. So again, here's our sample space. Fair die, so we have 1, 2, 3, 4, 5, 6. Okay, and the number in that is 6. This is a uniform sample space because each of these outcomes are equally likely to show up, assuming it's a fair die. So what we can do then is we'll define some events. Notice that we have the OR here. So what I will do is, up here, we'll say that this is E, which is an odd number, or a number greater than 2, which is we'll call F. So over here, I will list them out. I have E is an odd number, so I have 1, 3, and 5 is an odd number. And over here I have F, number greater than 2. So notice it says greater than 2, so that means that it doesn't include 2. So it's got to be 3, 4, 5, and 6. So there's 3 points in E. There's 4 points in F. And let's look at the intersection of E and F. So there's nothing, there's no 1 in here. There is a 3, and there is a 5. So that's 2. So using our addition rule up top here, I have probability of E union F. So again, there's the or. So it's either E or F is the probability that we want. So I have the probability of E union F is equal to the probability of E plus the probability of F minus the overlap. So because it's a uniform sample space, I can do the probability. Here's the probability. The probability of E is the number of elements in E over the number of elements in S plus the number of elements in F over the number of elements in S minus the number of elements in the intersection E and F over the sample space. So I get 3, 6 plus 4, 6 plus, oops, and I gotta be careful, don't add it. It's gotta be subtracting it. So take away 2, 6. 3 plus 4 is 7. Minus 2 is 5. So therefore, the probability of rolling an odd number or a number greater than 2 is 5, 6, or approximately 83%. Now here is a question. What if E and F are mutually exclusive? So that means if I wanted to look at E union F, which is the probability of E plus the probability of F minus the probability of E intersect F, well, since this is mutually exclusive, it means that the intersection of E and F is empty, which means that the number of elements in E and F is 0. Exactly. We can use the same formula except for E and S. Yes. So this is 0. So that means there we go. And again, if E and F are mutually exclusive. else could we do is we could also say that this is a special case of axiom 3. Because in axiom 3 that we had n many mutually exclusive events. In this case, we're just working with 2 mutually exclusive events. So over here, I'll just draw the little box. Here's our sample space, which means then that E and F are mutually exclusive. Perfect. So here's a question. So, for instance, we have, let's say, we have a Roman. His name is Grumio, and he's buying a ticket. He's buying a lottery ticket. To support Caesar. And Grumio is asked by his friend Marcus what he thought his chances of winning the 1,000,000 denarii was. So Marcus, his friend, he asked Grumio what his chances of winning the jackpot was. And Grumio said, is less than 1. Yes. Grumio says his chances of winning are 50-50. He reasons that he's either going to win or he's going to lose. What's incorrect about this? So basically, Grumio says he's bought a ticket and his chances of winning are 50-50, which is he's either going to win or he's going to lose. So he's saying that the probability of him winning is the same probability of flipping a coin. He's conflating probability with outcomes. Yes. Yes. He's conflated, actually, what he's done is with his outcomes and the actual outcome of the lotto choosing. The number depends on how many people picked a ticket. And that's an interesting question as well. Exactly. It depends on how this lottery is set up. So what we're going to say is that win/lose of him is not part of the sample space. It's not an outcome. What the win and lose actually is so actually it's an event. There's also 6. Yes. So again, if it's a lottery, so what the win and lose actually is an event. So the probability of him winning is equal to the number of outcomes where he wins over the number of tickets there's only one winning ticket, so it would be 1 over the number of tickets. And using our so if we're going to assume that it's win and lose, so if he loses, what we can actually do then is we can use the complement rule, and that would be 1 minus the probability of him winning. So yes, what he has done is he conflated the event with the sample space, with the outcomes of the sample space. So again, it's very important to understand that when we're talking about what an event is and what our outcomes are of the sample space, and again, it's a common fallacy that some people could run into. So again, we don't want to make that same mistake. Okay. Good. I'm glad everyone could spot that. It definitely did not reflect with our real world experiences of people 50-50 basically buying a lottery ticket and winning half the time. You would expect to win half the time if it was 50-50. So let's look at an exercise. We have 8.5.2. What I'll say is that we have two events E and F. We're going to say that the probability is 0.3. We have the probability of F is 0.75. Probability of the intersection, nice, it's a quarter. So the first thing that they ask us for is for the union. So again, we can use our addition rule. It's the addition of the individual probabilities. Oops. Minus the overlap. So you have 0.3 plus 0.75 minus, oops, the 0.25. Okay. So the 0.3 plus the 0.75, that gives us the 1.05. Plus we need to subtract the 2.5, which leaves us with the 0.8. Hopefully I've done the addition correctly. The other way that you can think of it is the 75 cents minus the 25 cents leaves you with 50 cents. And then you have 50 cents plus 30 cents, which gives you 80 cents. Okay. Let's do E complement. So that would be 1 minus the event E. So it would be 1 minus 0.3. So that should equal 0.7. The probability of F complement is 1 minus 0.75, which leaves you with a quarter. Okay. Oops. Now we have the E prime or E complement union F complement. And we don't have a formula for this. So this is why we needed our set theory. So what we can do, what set law can I apply to E complement union F complement? Which law can I use? Can't you use the answer from A and minus it from 1? Yes, but why can I do that? And I think you're right. Let me just take one step. So I'm going to use De Morgan's law. So what I'm going to do is I'm going to use E intersect F. And then I have the complement. So if I go backwards, I'm applying De Morgan's law. So that would be E complement. The intersection changes to a union. And then I have F complement. So there it is. So what I have there instead is 1. I can now apply the complement rule, which is 1 minus the probability of E intersect F. Yes, we can use De Morgan. So this was using De Morgan's law. And then from here to here is my complement, my probability complement rule. So now I can do 1 minus 0.25, which gives me 0.75. Okay. Yeah, so what I've done here is I've just had to rewrite it. I don't have anything do any rules, so I've manipulated it. I just applied De Morgan, and then from there I see I have E intersect F. This is something I do know, and just using the complement rule, I have 1 minus the intersection, and so it should be 0.75. So let me write over here E. Let's do the probability of E prime, or E complement, intersect F complement. And we can do the same thing again. We can apply De Morgan's law. So I can be writing this as E union F complement. So again, if I apply De Morgan, the complement comes down, so there's E complement. The union switches to an intersection, and then I have F complement, and there it is. So that's by De Morgan. And same thing again, I can use the complement rule because I have this complement up here. So 1 minus E union F. Now I can do 1 minus what I found up here in part A, so 0.8, which leaves me with 0.2. So if you want to have a similar exercise, check out 8.5.4, and you could try, for example, 8.5.6 in the textbook. Okay, I think we've covered enough material for today. I hope you all enjoyed the introduction to probability. Again, this is something that I have seen a couple of times before. And I can just quickly run through what we had covered in the last couple of minutes, or in the last 2 lecture periods here. So again, we understood what a uniform sample space was, that we have a sample space, it's a universal set, or all the possible outcomes that we want are of interest in an experiment. They're equally likely. Again, be very careful that people don't mix up that events and the outcomes in a sample space. We looked at the probability in a uniform sample space, that if they're all equally likely to occur, then you end up just counting the outcomes that you want over the total outcomes. We used a fair coin as an example of a sample space, a uniform sample space. We looked at a deck of cards as also an example of a uniform sample space because each of these are equally likely, assuming that if I take a deck of cards, maybe I should shuffle them. That any card I pick out of here is equally likely as any other card in the deck. So there's the Ace of Clubs. What was the probability of me picking an ace? It was 1 in 13. There again, it was a coat check problem where we just kind of wrote this all out. Again, we could just write them out, but wouldn't it be nice if we had some more elegant way of counting outcomes without having to do this brute force method of enumerating all the possibilities? So stay tuned for that. We then covered the axioms of probability. We had the Axiom. Again, basically it's a square with an area of 1. We said that the sample space has to be 1, that an event has to be non-negative. The probability of an event has to be greater than or equal to 0. So we can't have negative probability. And from 1 and 2, this gives us this implication here, which is that the probability of an event must be between 0 and 1. Okay? So if you have something on the test and you write me a negative number, or you give me a probability that's greater than 1, that's wrong. And lastly, for the axioms, if the events are mutually exclusive, then the probability of the union of all the events is equal to the sum of the individual event probabilities. We then looked at simple probability rules, meaning that we have the complement rule here, where if you know what the probability of E is, you also know what the probability of the complement is. We had the addition rule, which again is basically an extension of our set theory. And there was our principle of inclusion and exclusion for 2 sets. So again, it's the probability of 2 events, E union F, is equal to the individual probabilities minus their overlap. We did an example there. And we did an exercise here where, again, some of our set rules that we had done with De Morgan, or using our ideas of, oh no, it's just De Morgan in this case, came back in. So again, when you were asking me, why is this useful? Because basically what we have done using De Morgan or complement probability rule is we've come out with some more inference from this data here. We were able to infer each of these other probabilities. Thank you everyone for tuning in, and I hope to see you tomorrow on Tuesday. Again, I will get back to marking those tests, and I hope you have a great night. Take care, everyone.